they only have 5 forks, but each philosopher needs 2 of the forks to eat at any given time. So the issue then is sharing the forks between them so that they never get deadlocked in any way, and they are all able to eat without any one of them being starved, like his neighbor is always eating, and every time he like stops thinking to go for the forks, they're using them, so he never gets to eat. So, yeah. I'm just gonna, so this is essentially the example. What the philosophers are the outer circles, the forks are the little black ones, and then the table is the yellow in the center. And what it is, each philosopher is blue if they're thinking, but then when they become red, they decide they want to eat, and they're going to try and get forks. And then once they're green, that's when the forks are over to them and they're eating. And so essentially this system is just illustrating the way it works is the guy that becomes red first, he'll take the forks, start eating, and then the next one who decides he wants to eat, he becomes red, he'll get the forks next, and it just repeats in that process so that each guy is able to eat, and as you can see, it's not becoming deadlocked. I can just leave this up here, and they'll happily keep eating and sharing the forks forever. And so a couple of questions. Do you know who invented this question in the first place?
So another question, but if we look at the bottom, and then see that how it's green, and now he's eating with 1 fork.
There's a little delay in the program that he's not actually eating at that time.
So that's delay. All right.
Yeah, yeah. Sorry, I forgot to mention that. But he's not actually eating at that point.
Just drew up the other one thing.
Oh, the jack stuff?
Yes. Can anyone give me an example of deadlock in this? Like, what would be happening for deadlock to be taking place?
If a deadlock would be taking place if one person has both forks in front of them but is not eating, because then he would not or was thinking. So he's holding both forks just for whatever reason, and he's not eating the food. Therefore, when his state changes, the person next to him can't eat the food because he'll be missing a fork, and so on and so forth.
Not exactly. We assume that like he'll always be eating when he has the forks and puts them down when he's done. Like we assume everything's functioning correctly there.
Well, what if he doesn't put the forks down until after he's declared?
Until after he's what?
Sorry, I'm just remembering from the next activity we had in class. So it was, what if the state change from hungry is after he puts the forks down, right? Because he's I'm no longer hungry, and then he puts the forks down. So that means it's the opposite of he's no longer hungry and he keeps the forks in. Because then his state has changed, but he still is holding the 2 objects. So the person next to him can't pick up forks. When his state changes, needs to change.
Yeah, I guess that would work. All right. And an example of live lock in this? Anyone know what live lock is and what would be an example there? Okay, well, live lock is essentially similar to deadlock, except that when deadlock no one can move and they're all stuck. Live lock is something is still going on, but like there's no actual progress being made. So as an example, say if every philosopher was supposed to pick up their left fork at the start of it, so they'll pick up the left, they couldn't go anywhere, so then they put that fork down, and then say they try to pick up the right fork. Well, they all pick up the right fork, but then they still can't go anywhere, so they put that down left and just go back and forth, and that would be live lock.
So the main issue with this problem is that if each philosopher picks up 1 fork and is waiting for the other fork to become available, all of them will keep waiting like that forever. So your classmates have used a special structure in their codes to implement the mutual exclusion for the forks. And so they were able to resolve that deadlock situation.
So the only way they can pick up forks is if there's 2 available?
Mm-hmm. Yeah. Okay. And there are many solutions to it, like what the guy who invented it, Dijkstra's original solution was that each of the forks have a hierarchy, like 0, 1, 2, 3, 4, and then a philosopher can only pick up the higher number of their 2 forks. So in the beginning, 4 of them will pick up a fork, and the last guy can't pick up the fork, but so you have 1 fork free and 1 guy without a fork, but then the guy who has the, who picked up, I have trouble like seeing this without it in front of me, but the guy who picked up the highest fork can then pick up the lowest fork because that's still the highest one left, So he'll be able to eat and then put his forks down, and then the process will repeat that way. Another solution would be having a token that, like, say a waiter gives to each guy, and that he'll only be able to pick up forks when he has that token. So he gives the token to one guy, he starts eating, the token moves over 2 spaces. That guy can also pick up both of his forks, and then it moves around and just keeps going that way. That's another example of how to solve it.
Okay, very good. Let's applaud the presenters.